What is up, guys? I am Hannah, and this is my wonderful friend Gwen, and we are both chemists. And today we wanted to just kind of talk to you a little bit about, just have a little chat, have a little hangout, talk a little bit about what it's like to be a chemist in the real world of chemistry and industry and academic research, and some tips and tricks that we have collected over the few years that we've been working professionals. I'll just jump into my experience. I actually started my first internship. It was an undergraduate research experience when I was 16, and I had gotten a recommendation from my chemistry teacher in high school to go work at University of Texas at Dallas, and it was a really cool experience because I got to learn about biofluorescence and using fluorescent tags on RNA molecules to study the activity of a component of the HIV, so the virus, and getting to understand more about the physics behind that and how you can use UV light to kind of understand what's going on in a dynamic sense. And then when I was in college, I kind of honed in really on academic research. I thought that I wanted to go on and get a PhD. And so I did a few different research terms, one with computational biochemistry, one with computational biochemistry focusing in on molecular dynamics of proteins, the other one focusing in on ab initio calculations, basically understanding the fundamental thermodynamics behind how proteins fragment when exposed to oxidative stress conditions. And then all of that gave me some really cool insight into how computers work, how supercomputer clusters communicate with each other, what kinds of considerations need to be made to simulate biomolecules in space or in a vacuum, and how that deviates from reality. And it gave me the insight that my senior year I want to do some other research. So I went and worked in an agricultural biological engineering lab, and that's where I actually looked at UV absorbance of an enzyme, actually, to look at its catalytic activity to break down something called lignocellulose. It's a component of a lot of woody fibrous materials, and the idea was to try to understand how to improve the efficiency of breaking down these kinds of materials and turning them into biofuel. So those experiences led me into my graduate experience, and I decided that I wanted to move into synthesis and kind of materials. So I went to UC Berkeley and started my PhD, and it ended up becoming a master's, which is totally fine and just a choice that I needed to make given the circumstances going on in my life at the time. I learned a lot in that program, and it taught me a lot about how to be a self-driven learner and how to be extremely organized and very efficient with my time. And the fact that there were some failures along the way taught me lots of things about how to just be a better working professional. Different boundaries and limits I needed to set for myself to be functioning in a professional way in an environment when things are not always going your way. It taught me a lot of important interpersonal skills as well, and overall my project did not work, but I did.
That happens most of the time.
That is true.
For research that you do in academia, most projects are going to be a failure, and it just, what you learn about is what's important.
Yeah, that's true. I guess PhDs, probably a lot, like probably 2/3 of PhD theses are are just like where people spend 5 years tackling a series of problems and learning about how to tackle problems effectively, but at the end of the day, their thesis isn't groundbreaking. It's just adding to the body of knowledge of, like, Thomas Edison's light bulb, finding 99 ways that it didn't work before you find the right one. Somebody will come along and their claim to fame will be that they found the holy grail of that topic, and it turns out that they just basically got to absorb all of the information from all the other failed theses.
Absolutely.
Yeah.
Which is why when you read an academic paper at the end, you have 2 long pages of teeny tiny font of all the references that they use.
Yeah, for sure. Yeah, so then after all of that, I decided, okay, well, I'm going to use my chemistry degree to go work in industry and just take a crack at that. And my first job, I worked at Mary Kay Cosmetics. I was a contract chemist, which the rules for contract work are a little bit different from being a full-time employee of the company. But I did learn a lot in that experience about medical type research, the kinds of documentation you would need to successfully create new methods, implement new methods, and to what extent you know those methods. Like how good is a value, and is it under the FDA limits for a certain amount of preservative or active to be in a formulation product that's going to wind up on somebody's skin. It's got to be good, it's got to be safe. So those were the kinds of things. I actually used analytical chemistry to work on projects that got that information for the company. And then now what I'm doing is actually I am working as a paints and coatings chemist at Vorvog, and I am learning so much every day about just rheological behavior of paints and coatings, and how they spray, and how all of the different factors involved in that pretty complicated system actually contribute to the overall color and effect, and how that winds up on cars.
Fun stuff.
Yeah, so I don't know if Gwen wants to say more.
Oh, sure.
We've got 12 minutes on the clock here.
Well, basically, polymers are everywhere. Polymers are amazing because they are so multifaceted and touch on any area in industry, like automotive coatings. Anything that is synthetic is related to polymers. So fabrics, coatings, foam in couch cushions, it all touches on polymers, which is one of the great reasons to get into polymers if you like solving lots of different types of problems and not keeping yourself grounded in one little industry, something that's so niche. If you get into polymers, you can go anywhere. I mean, my first internship was coatings related for oil pipelines, so a coating that goes on metal. But after that, I got into flame retardants that go into plastics and into cushions for cars and couches, things like that. So that's also related to polymers because of the foam component and the plastics component. And
You mean we're sitting on chemistry right now?
exactly. We are sitting on chemistry. We are surrounded by chemistry.
Who would have thought, man?
Exactly.
That's what I've been trying to convey in this entire channel.
This extremely soft blanket.
What is that made out of?
I don't know, but it's synthetic because it's so
Yeah.
incredibly soft and affordable.
Yeah.
Since it's synthetic, it is a polymer. This is wool, so it's not a polymer. Or at least I don't think it is.
You should have gotten an acrylic blend.
I don't know. I mean, it is pretty soft, so there might be some acrylic polymer in here, but I'm not sure. I think it's mostly wool.
This one's probably synthetic. There's probably polymer in there,
Probably. Yeah. Oh, this blanket might be cotton.
too. It's acrylic.
Oh, okay. So also
Also a
acrylic.
polymer, yeah.
Also a polymer. The floor underneath us is, I think, some sort of...
Polyester, probably.
Yes, exactly.
Yeah.
So everything around us is polymers, which is amazing. They're just everywhere. Chemistry just surrounds us, and most of it is polymers.
That's why I want to move into it eventually.
Yeah. Well, you basically are, because you're in coatings, and that is a polymer reaction. We've got the polyurethane, the polyacrylic, those kinds of polymers.
Plus you've got all the resins that make up the backbone structure of
Exactly.
the the film, essentially. It just keeps it strong and sturdy.
That's what makes it durable.
And it also gives it its flexibility for impact resistance.
Yeah, so you look for different types of monomers or families of oligomers, which are basically short polymer chains, so a few monomers that have combined. And that's the starting point for your coating, but then we add what we call in the industry catalyst, even though it reacts into the backbone, is not a catalyst.
It's a reactant.
It is a reactant. Another term for it is hardener. You're taking the paint, the coating that is wet and liquid, and you are adding a hardener or catalyst to it, and that's what helps it cure. You're baking out some of the solvents or water that is in it, but what helps give it its durability and its strength comes from the cross-linking reaction that occurs when you add hardener. So, fun stuff.
Yeah. And then do you do any academic research?
I did, yeah. I did some undergraduate research in an inorganic chemistry lab for adhesives, which are also polymers. Almost all adhesives are polymers, which is fun.
Would you call that a coating? Or is it still just
I don't think I would call that a coating, but the chemistry behind it is very, very similar.
Okay.
And how coatings bind to a surface is often the same way that an adhesive binds to the same kind of surface or combines two surfaces together. It's the same kind of mechanism of the polymer kind of etching itself into the surface to bite into it and stick. That's how a coating sticks to whatever plastic or metal you apply it to. Or fabric or flooring or any other kind of material, although for the most part she and I have experience with coatings going on metal or plastic.
Yeah.
But there are options, they can go anywhere. But yeah, it's a similar kind of chemistry. And that's basically where my passion for polymers came from. And I highly recommend, while you're an undergraduate student, to talk with your professors, because that's how I got this job at the university, was by just talking with my professor. And people will tell you, talk to all your professors. You don't have to. Just pick someone that you like.
Yeah.
1, 2, 3, focus on those kinds of professors that you're most excited to learn from, and talk with them. Go to their office hours, send them an email occasionally. I mean, professors are busy, but it's their job to teach you. So they make time to answer your questions. I mean, don't email them every single day, multiple times a day, but once a week, something like that. That's totally reasonable.
Yeah.
I went to this professor's office hours. I visited him after class a lot if he was open to it. And I emailed him several times, and I stayed in touch with him over the summer. And during that summer break, the first couple weeks of that break, I was looking for an internship, which you really should be looking for an internship sooner than right at the start of summer break. But I told him that I was looking, and he asked me if I wanted to go work in his lab, and I did the next week, and just worked with him all summer on this adhesives project that was not successful at all, as expected, because if 2/3 of PhD projects fail, probably 95% of undergraduate projects fail, because the ones that would have been successful would have been taken by the PhD students in that lab. Anything that has a chance is not going to be given to an undergraduate student, or at least it's not likely to. Like, Hannah got a paper.
I got a paper. So
that's not common. Most undergraduate students don't get a paper even if they spend multiple semesters working in a lab. But don't be disheartened by that. So having a paper is awesome, but not necessarily expected when you're going into industry or to get your PhD or master's.
Yeah.
But yeah, so my project was not successful at all, but what I got to do was I was making an adhesive that was disulfide based, so the backbone of the polymer had a lot of sulfur to sulfur bonds, and supposedly these are sensitive to electricity, and by that I mean they should be breaking up if you expose them to electricity. So we were trying to make an adhesive that could be broken apart if exposed to electricity. So that would be fun if you had something that you wanted to like stick onto a surface and not have it be a permanent bond. So something that could be removed at whatever time of your choosing. You could just expose it to a little bit of electricity and it'd be broken apart. So anything that would be temporary, like you're just trying to stick a camera on the side of a ship or something like that, and you just want it to be a temporary bond. That's what we were trying to do. So we were making this polymer with disulfides in the backbone and exposing them to electricity, but we got some burning to happen. That was fun.
No, do tell.
Got to learn a lot of different kinds of chemistries, not just about like polymerization reactions, but how adhesives work, how to test adhesives. One fun thing about working on a project that is doomed to fail is that you can do whatever you want to it. So I was coming up with all sorts of weird methods for how to expose an adhesive to electricity and how to test how effective it was. And one of the methods I was using is I was taking this polymer and I'd have like my starting point that I was not going to expose to any electricity, and I just set it to the side. And then I'd have the adhesive that I was exposing to electricity, basically just by taking aluminum foil and putting the adhesive in between these two sheets of aluminum foil and touching them to a battery that I'd rig up in a safe method. And then I'd scrape that stuff off after the exposure, and then I'd take my two samples, the one that hadn't been exposed to electricity and the one that had, and I'd make a little solution to test with NMR, and then I'd see if the polymer had broken apart at all. One of the fun things that you can do with polymers to see how far the reaction has progressed, how big the polymer is to see how wide your peaks are in an NMR. And I could tell that if I was breaking this adhesive up at all, that my peaks would get more narrow, which they kind of did, but on a very qualitative level.
Oh, okay.
So that was loads of fun and gave me lots of good skills. I think I did 3 semesters in the lab, 1 summer and 2 times during the year. I did another summer too, so 2 summers. I got paid for it, which was nice.
Yeah.
Not all undergraduate research experiences are paid.
Yeah, for sure.
Especially if you're working for the school. If you get a job with something in industry, you're going to get paid. If you're doing anything that's chemistry related or engineering related, you should get paid. It's not like if you go into communication and you're working for some newspaper company and it's an unpaid research experience, which is still beneficial, but it's nice to get paid when you have all those student loans. Mm-hmm. So this part was paid, which was awesome. No paper came out of it. No paper was ever going to come out of it. But still, it was fun. And the reason I got it is because this professor liked me, because I talked with him a lot and was interested in what he did and what his research was like, not just the things that he was teaching about in class, but what he researched in his lab. Because that's what professors do typically to make their money. They're not just teaching, they are running a lab. And sometimes what they're teaching about and what their lab is related to can be different. So he did inorganic chemistry is what he taught, but he was making adhesives. So there's a lot of inorganic chemistry related to adhesives, but it's not necessarily the first thing you think about when you think about inorganic chemistry.
Yeah, okay, so guys,
We talked about polymers.
we talked about polymers, we
Chemistry.
talked about chemistry, we talked about some suggestions for how to get the research experience of your dreams. And so basically, even if you feel intimidated, go ahead and give it a shot. Talk to your professor of choice, or whoever has the most interesting personality, the most interesting research, or the most interesting class. Come over and talk to that professor after class. Email him periodically or show up to office hours and ask questions about his research. I'm saying he, but I mean he, she, they, whoever. And
just take the time to get to know your professors and make that connection. That way you have a foundation for joining their lab in the future if you wanted to. You could either, well, I got approached and asked to join this lab, but if you want to join someone's lab, just take the initiative and ask. And if you already have that foundation there, that relationship has been built, then you're all the more likely to be accepted into that lab.
Yeah. And then the other piece is when you get a research experience or an internship, be sure to soak up the experience, and even if a paper doesn't arise out of it, just give it your best shot and ask questions of your colleagues, try to learn as much as you possibly can, and get marketable skills out of it, you know, things that you would want to be able to explain to a potential employer or a potential grad school that might want to hire you to be a teaching assistant and a graduate researcher. Try to find the skills that will help enable you to pursue the career of your dreams. So those would kind of be the strategies that we'd suggest. And be proactive and try to get going on looking for opportunities for internships and research experiences for undergraduates, also called REU is the acronym. Try to look for those early because, like in the fall semester, so that you can get it in the summer, because a lot of those positions are pretty competitive and they are great learning experiences, and try to get at least one before you graduate. So, yeah. Thanks for tuning in to Kisscrew Chemistry Help, where you are surrounded by very talented chemists and very good friends. So, tune in next week and we'll have more to say about the Maillard reaction. All right, bye guys.